Okay. Resistors. These are the main resistors right here that you'll find in electronics. Okay. They're these little cylinders that look like that, and they're really, really small. So here's a circuit board. Okay. You guys see all these little resistors?
Those are all resistors?
Yep. Most of them. Okay. Now resistors, they decide how much current is going to flow. Okay. They're like little gates. Okay. Some gates let a lot of current through. Some gates let just a little bit of current through. Okay. These are resistors too. Okay. Some light bulbs let more current through than others. Okay. The really bright ones. Okay. Then we're talking wattage and all of that. Okay. That's a totally different thing. We're not even going to get into what watts are today. All right. But you guys actually already know from mechanics. We're just going to apply that to electrical later. Okay. The heating element in here is also a resistor. And then what's the resistor in there?
The twisty thing.
The twisty thing, the motor. Okay, now the buttons behind, the buttons control what? The speed. The speed is controlled by how much current flows. How much current flows is controlled by the resistors behind the buttons. Okay, now behind all of those buttons, there are a bunch of these. Okay, each button's got its own resistor, as a matter of fact. Okay, so behind the high speed button, where the motor is going to go the fastest, there is a low resistance. If we want the motor to go slower, there is a higher resistance behind that button. Okay, those buttons are switches. They turn on and off the current. Okay, hang on a minute. All right, now these are our main resistors. They are carbon compound resistors. All right, and depending on what's in here, they will let different amounts of current flow. Okay? The colored bands actually identify how many ohms each resistor has. Okay? Ohms is the unit. Next to resistance on your little chart at the top, write impedance. If you see that word on UT, on your test, on your quiz, on your homework, impedance is resistance. They're the same thing. Okay, the variables are, capital R. The unit is ohms. Just write out the word for now. I'll show you the symbol in a second. Okay, now if you're going to design, let's say if you're going to design a flashlight. Well, probably not a flashlight, because a flashlight, the bulb is the resistor. But if you're going to design a blender, you're going to have to choose which of these are going to control the motor speeds. Okay? You're going to have to know which ones to use if you're going to do that. Okay? Here's another circuit board. This, I think, came out of a computer or something like that. All right? And you've got all these little circuits. Do we want high amounts of currents to flow in little computer chips?
No.
No. That's what'll burn out your... You can fry a motherboard, is what they would say. Okay, this is maybe a piece of a board here. Okay, if you get too much current, you fry them.
So do resistors like eventually burn out?
Well, a resistor can burn out if you overload it. Sure. Okay, they don't really burn out like a light bulb, though. No, they're meant to last and last and last. Okay, but you got to remember that a light bulb is a resistor too. Okay. You're a resistor. We'll find out here in just a second. Sounds like something Connor would say.
No, you're a resistor. Yeah.
Okay, so let's look under the doc cam here for a second and fill in some notes. Okay, so we said the variable is R. The unit of measure is the ohm. Okay, or plural, ohms. Okay, now the symbol is going to be like that.
Oh,
that symbol is omega.
Wow, that's so cool.
I know, isn't that fun to write?
what about alpha?
Wait, I
Alpha's
can't
used
even
for
see
other
it.
things.
Oh, yes, I can.
Okay.
Yeah, I've seen this.
Omega. Alright, now let's fill in some of our circuit diagram things.
It's like
So
the
when
McDonald's smiley.
we're not going to do any circuit diagrams today,
That's
but
fine.
this indicates a battery. current, if this was a wire, a current would be an arrow. Okay? That's just going to indicate the direction. And we might say, okay, that's 5 amps or something like that running in that direction. So it doesn't really have a symbol, but sometimes we'll use an arrow. Resistance is a sharp, squiggly line. That's a resistor.
Does it have the break in it, or did you?
That's just because of my pen. No, there's no break in there. So, can you guys see that? Oh, this is like a highway for charge. It's straight. Okay. Oh, look, we met resistance, right? Okay. The symbol actually makes quite a bit of sense. That squiggly line. Okay, so in this right here, I'm going to show you with the multimeter how to measure the resistance of some things. And I want you guys just to kind of take some notes so you get an idea of what the values actually mean in the real world. Okay, so let's start with an extension cord. So write down extension cord. And we can measure the resistance of anything, okay, using a multimeter. This is my favorite multimeter. It's a Craftsman, right? Little Craftsman commercial. Okay, now if it says that right there, that means the resistance is too high for it to measure. Okay, so what's that mean about the resistance of air?
It's
Really
high.
big. Okay, it's too big for the multimeter to even pick up. Okay, now if I connect this here, okay, that's the ground portion of the wire, and then I take this and connect it right here. You can see it instantly is trying to read the resistance, okay, and I'm not getting a good connection.
How come it's bouncing from like such high numbers to such low numbers?
Well, because I haven't connected it solid yet. Okay, so there we go. Now it'll kind of stabilize. It'll kind of fluctuate for a minute. Stabilizes on 2.4 ohms. Okay, that's an extension cord, 2.4 ohms. Now the length of the extension cord is going to change the resistance. Longer cord, more resistance, you'll find out in your homework assignment. Okay, but like a lamp cord or something like that, it's going to be a couple ohms. That's a very low resistance. Why would we want a low resistance in wires?
Because you're transferring stuff.
Okay, a wire is a highway for charge. Okay, we want charge to flow easy in that highway, right? Okay. How about some other things? Here's just a simple light bulb. You guys see that all right?
Yeah.
That's a light bulb. Okay, now I can take these two test leads, and this light bulb is 2.7 ohms. So put small light bulb in your notes. Okay, and that's about the same resistance as that whole wire, huh? Okay.
Is that because there's like a lot of power that needs to go to that one little light bulb?
Yeah, the filament in a light bulb is a very, very thin wire, okay? And when the current goes through it, it meets resistance because it's so thin. And it goes through that and it creates heat and light, okay? That filament glows because it gets so hot. All right, look at this. I've got another light bulb here, but with wires connected to it. Okay, if I connect this, oh my gosh, nothing happens. What does that tell us?
There's no resistance.
Tells us the resistance
whole
is too
lot of
high to
resistance.
measure. What can we conclude?
That's dead.
This light bulb is burned out. Okay? So when you take your car in to the mechanic and there's an electrical problem, they often use an ohm meter to tell what the problem is. Because if they connect to a certain circuit, say your window motor, this side of your window motor and this side of your window motor, okay, the wires, they connect and it says that means that little unit is burned out. Okay? If they turn the switch on and it doesn't read a resistance, they know that thing is fried. They're going to have to replace it. Okay, a couple questions. Connor?
Can you use that water, so like if you stuck one in the water and the other in the water?
We'll do that in a second. Mitchell?
So what does it do? Like send electrons through it or something? Like send a
Yeah.
charge?
Little current. That's right. Okay, Mitchell, or Connor just asked about the water thing. This is cool. Okay, so I'm going to take a couple paper clips here and put those in the water. Get a good way to connect here. And then we'll connect the test leads onto those. That's for you, Sarah. Okay, so can you guys see that screen? Nice thing about this multimeter is it is an auto-ranging multimeter, okay? So this little number, which you can't see right there, changes, well this little letter actually, okay? And that's a K. What's K stand for in the metric system?
Kilo.
Kilo. Okay, so right now it says 3, let's say it says 4 because it's fluctuating. So let's say 4 kilo ohms. So how many ohms do I have right here? 4,000 ohms. Alright? So that's like, I'm going to say that's 1.5 centimeters of water. So the resistance between 2 points, 1.5 centimeters of water, 4,000 ohms. That's the highest resistance we've measured yet, right? Okay. Oh, let's go to the beach. Ready? Salt water. Here we go.
I feel
Watch
like it's
and
gonna
be
go down.
amazed.
It's gonna go up.
It's gonna
Get down, baby.
Holy cow.
go down. Ooh, I
It's
know
still on kilo ohms right now.
That's a lot of salt.
I put a lot of salt in there.
I don't think you have to resist it.
Drink it.
Okay, now I'm going to dissolve the salt. We're down to 200 ohms. Uh-oh, now it's mad because I've made the resistance too low. Or I've dropped it too quick. I wasn't happy about that. Okay, so look at that. Now I'm down to only 200 ohms. So I went from, what was it, 4,000?
Yeah.
So I was at 4,000, now I'm at 200. How crazy is that?
Wait. Because
Okay.
the K went away?
Yeah.
The K went away. Yep, now it's just on plain old ohms. So what's that tell you about shock risk if you are wet, for one, or been swimming in the ocean, too?
It's more dangerous if you're in the
If
salt
your
water.
ohms go down, your current goes up. So yes, you could get shocked a lot more easy.
So if
Alright, that's why most electrical shocks happen where?
The ocean.
water.
Bathroom, water, yes.
Wait.
Okay, wait, hang on. Let's look at this. We can measure the resistance of an entire person. So if I grab these leads right here, it gets mad for a second, and it freaks out and changes scales.
Wow.
Okay, right now it's saying that I'm 1,000,000 ohms. Now it says 1.1 in a capital M, that's mega. Okay, now the resistance of a person is actually more like 500,000, so that's not super accurate right there. We can try this one.
You're broken.
Okay, we'll
Why would
change
it?
that
Why would that
ohms.
read differently?
Does it matter which way you connect it to?
Oh, is it because you're like grounded or something?
Okay, now it's saying 0.7 mega ohms, so that's a little bit more reasonable.
Like 700,000.
700,000 ohms a person. Okay, now what if I just got out of the ocean, I've been swimming?
Probably go up or down.
Good.
I'll go down to about 100 ohms is what I hear. Okay, I have not tested that, but I read that in a textbook. It's got to be true, it's in a textbook. Not. Okay, 700,000. So yeah, electrical shock. Okay, that happens most commonly in bathrooms because the resistance of the person is way lower because they just got out of the shower, something like that. Okay.
Wait, so if the resistance of like water is super high, why is it like why do people get electrocuted so bad in normal water? Like that's what I'm not understanding.
Well, what we're talking about here is dry skin versus wet skin. Okay? Now your skin's got a lot of salt on it, right?
Sure.
Okay? Salt is an electrolyte. Okay? Travels very well through it. Now, if we're talking about huge bodies of water, let's say you're at this end of Highline Lake. Okay? And at this end of Highline Lake gets struck by lightning, the actual surface. Okay, is that going to do anything to you? It's actually not. You're going to be totally safe. Okay, now if you're here and the lightning strikes right next to you and hits the surface, could you get some shock? Probably. Okay, but that body of water is huge, so that's not really a danger. All right, but your resistance as a person goes down if you're soaking wet. And if you are soaking wet in salt water, it goes down even more. Mitchell?
Is it like logical to fear for your life if you're in a little boat on the lake when it's lightning out?
Well, I
Like
mean,
in
if you're on a
fishing boat.
you might have more risk of being shocked because you're the highest thing in the water,
So
right?
you'd be safer if you jump in
Even
the
if you're dry, like you haven't been in the
Maybe.
lake.
Safer if you jumped in.
What a
water.
concept.
Reasonable question.
Yeah, it is a reasonable question. Okay, let's measure the resistance of this bulb. This is weird. I don't know where to connect it. What do I do? What do I do?
Just touch it.
Okay, I'll just touch it.
Well,
Yeah?
no.
No? Okay, how about here?
No, that's not a part.
There and the bottom.
Yeah.
Here.
So that it goes through the filter.
Okay, this is an electrical contact for the lamp, okay? And then the other electrical contact is right there. You see the meter jump all of a sudden?
It was like, wow. There's something.
And we get 29.1 ohms. Okay, this is a 40-watt bulb. So a 40-watt bulb is 29.1, and it fluctuated a little bit. Okay, I have another one here. This is a 100-watt bulb.
Wait, what was the 40 watt? 29.1.
Okay, what do you guys expect to happen when I have a 40-watt bulb?
Resistance goes,
Down or up? Let's check it out.
so from 40 to 100 it goes up. It goes down.
Okay, that one's stabilizing at 10 ohms. So what happens here is this one lets more current flow, doesn't it?
So brighter.
Yep, it's going to be brighter too. Okay, let's look at these. These are little bags of resistors, okay, and they're labeled. You can tell the resistances from the colored bands. So this bag has got a bunch of resistors in the 1000 range, okay, 1800 kilo ohms right there. Or sorry, it'd be 1800 ohms or 1.8 kilo ohms. This one has got resistors in the hundreds of thousands of ohms, okay, and then these resistances are small, okay, 22, 27, alright, that's what's inside something like this. So let's take this fan.
It's a big fan.
You're noticing maybe that I'm not measuring the resistance when things are plugged in, okay? Resistance is always measured when there's no current flowing. All right, I'm not going to take this ohm meter and start connecting it when things are actually plugged in. Okay, so it's got a switch at the top. And to measure the resistance of something that plugs in, you simply do this.
Is that right, those versions?
No, I don't think so, but they're convenient for that. Yeah, that's a good question. Okay. All right, it's a broken fan, right?
You might want to turn it
Now your
on.
switch is off.
Oh, the switch is off. Okay, so really it's measuring the resistance of what?
The fan.
The
is off.
switch.
The air.
Air.
Oh.
Because there's air between the switch. Good. Okay. Now let's turn the fan to level 3, highest speed. Okay, I get 54.7 ohms.
How does it measure that?
Sends a little current through it and
Sends
sees
a
how
little
quickly
current
it comes
through.
back.
Yeah, and it's seeing how much is actually flowing.
How is that sending current?
Because this has got a little battery in it. This meter has
Oh.
got a little battery in it. Small voltage source. It actually takes 2 AAAs. Okay, some of them take a 9 volt. Alright, now let's go like this. Oh, you guys predict. I'm going to turn the speed of the motor down. What should the resistance do? You guys are smart.
Thank you.
Okay? Alright, the resistance, did it double?
Almost.
Okay, so what should the fan speed do?
Half.
Half? Okay, I'm guessing. That might not be quite true, but that would be a good
Roughly.
hypothesis, right? Okay. Speed 1, what'd the resistance do? went up some more, right? Okay, you guys see how that works? Okay, now I took apart a fan. All right,
Oh, I was wondering. What
this
that
is the
was.
same fan.
Don't stop.
Yeah, it is. Same brand. Okay, here's the hot wires. Those are coming in. They're at 110 volts from the wall outlet. Okay, and then we can get different amounts of currents to flow. Okay, here, this is going to be the on-off switch, right? Here's resistor 1, resistor 2, resistor 3. So what's actually inside this black thing that I tried to take apart but failed at? Those little resistors that I showed you on the screen and in the box up there. Okay, and they're going to decide. They're little gates that decide how much current's going to get through. Yeah, we tried to pry it open. I got my best physics 2 students in there trying to crank it open and couldn't do it. Okay.
It's a piece of plastic. Just
Here's a
flip
little electric motor. I don't know why I just did that. I just felt like it.
You should make a boat.
So since that motor's so little, if you plugged it in, would it set
If I
spinning?
plugged in the wall outlet,
No. If you put the meter on
let's
it.
plug it in the ohm meter.
Oh. Is
Okay.
there like a motor small enough that you could actually get the thing going?
Okay,
with
now
the
this
ohm
is a
meter?
3-volt motor, meaning they recommend that you hook it up to 3 volts and not 9. I just tripled the voltage. Let's say I operated it at 9 volts for a long period of time, what would probably happen?
We'd have too much.
Yeah, we'd kill it. Okay?
Poor thing.
Alright, that's pretty cool, huh? Alright, do I have anything else to show you?
Yeah.
Look at this. People make fun of me with this teapot because it has tulips on it.
It's adorable. Yes.
It's adorable, huh? Okay, let's hook it up to the multimeter. What do you guys think the resistance is going to be?
Low.
Very high.
Yeah. Low. I don't know.
Only 23.8 ohms. Okay? This lets a lot of current in. Things that heat are pretty low resistance because we need a lot of current to go through this to heat that plate up. Heating and cooling takes a lot of energy, right? You guys know that from your parents because they're like, shut the door when it's winter. Alright? And in the summer, right? Because
The door.
shut the door. Yeah.
Shut the door.
Using all of our electricity.
Out loud.
Okay, let's see. I got an entire spool of wire. It's like, it says it's 500 feet, but we've used some, so it's not actually 500 feet. You can measure the resistance of the whole thing by connecting right there and then to the end. Let's see if I can get a good.
It'd be higher than the shorter piece of wire.
Okay, what do we get?
I went for.
Look at that, low, 1.7 ohms for that whole wire. Okay. Alright, you guys have any questions?
Could you test? Sorry.
Okay, anybody want to grab these and see what their resistance is?
No.
I'll do it. Alright. I have a question.
Grip them tight. Oh. Whoa, whoa. It's saying that Emily is only... It's saying she's only 300,000 ohms.
It's not bad.
You're
It's
broken.
not very high.
High risk of electrical shock, this one right here.
You're broken.
Is it because
Okay.
she's so little?
Maybe.
Like really?
Good theory.
Okay.
Okay, Connor, you grab onto those.
Could you test it through the
Maybe
wires?
hydration.
There you
I don't
go.
know, other theories.
Oh, you should let me do that. I drink water.
Okay, Connor's got, 400,000 ohms. Okay, now it's reading pretty accurately.
Yeah. Okay.
All right, I'll pass this around. You can measure your ohms. What's up, Mitchell?
So like, a motor is not a resistor then?
It
Like-
is a resistor. All these things are resistors. Everything's a resistor,
Of some
except for
sort.
space, right?
Yeah, nothing can do with 100%
Yeah.
efficient.
Space isn't a resistor. Baisley,
So you could say that voltage moves current
voltage moves current.
and resistance controls how much current is like moved.
Resistance, yes. Okay. In fact, that question perfectly brings us into the next section here, okay? Which is this. Ohm's law. Current equals voltage over resistance.
Oh, it's still recording. Do you want it to be?
Oh, no, you can stop it.
Okay.